How many of you use a build system every day? Raise of hands. OK, let me see if I can get more of you to raise your hands. How many of you use Make? Maven, Gradle, Pip, Cabal, Rake? OK, so these are all examples of build systems. And a build system is a software that automates compilation of your projects and produces binaries. So today we'll talk about building a distributed build system at Google scale. I'm Aysylu Greenberg. I work at Google on Google's infrastructure. Today I'll talk about the projects that I worked on as part of the developer infrastructure team, which I think is really, really cool. In the past, I've worked on search infrastructure, and currently I work on Google Drive's infrastructure. So what does it mean to build a distributed build system at Google scale? Let's unpack this title little by little. So as we discussed, build system is a software that automates compilation of software. And so in order to answer the question of what does build system actually do, let's look at some of the two different scenarios. So a build system will do a build, or it can do a test. So what does that mean? So we'll have a project with some dependencies. On this slide, you see just a template make file, where on the left, right before the columns, is the target. And then we see the dependencies on the right side. And then the next line is the command you would execute to get the target. And so now the build system will take in this project with dependencies, and it would find the dependencies for you. So for instance, the main.c needs to be actually fetched from a remote server. And then once it found the dependencies and downloaded them, it will build this project with dependencies. And then it will emit binaries. And so now the build system will allow you to either download the build artifacts, or if you're interested in packaging them and deploying them on a machine and putting them in production, the build system will allow you to do that as well. And in the test scenario, it's very similar, except for now, instead of downloading the build artifacts, you're more interested in the results of the test. So you would run the tests, and then you'll get the results of the test, whether they passed or failed, or which ones failed. So we discussed about what build system does and what exactly it means to build and test. So let's talk about what it means to do this at Google scale and what kind of challenges are posed on a build system that is built at Google. So we have 30,000 engineers and over 40 offices. And so what that means is every single engineer needs to use a build system every day, many, many times during the day. And there is roughly 15,000 commits made by engineers every day, and about 30,000 commits per day made by robots. What I mean by that is that we'll have an automated script that will be committing code to the repository. And the reason we want to do this is because even with 30,000 engineers, there's still so much more work to be done. So if we could just automate that away so that the human doesn't have to do the boring, repetitive tasks, and they could just be delegated to a script, we would like to do that as much as possible. And so now all these commits will have to go through the build system. And the source code is 2 billion lines of code. And half of the code base changes daily. So what that means is every time a change through the code base goes, we need to build it, run the tests, and then ensure that all the failures are fixed before we commit the code. And there's roughly 5 million builds and tests that go specifically to the Build Rabbit system. Build Rabbit is the distributed build system that is part of the developer infrastructure, and we'll look at it in more detail throughout this talk. And Build Rabbit generates on the order of petabytes of output artifacts. And some of these artifacts are accessed in order to deploy them to production. Some of the artifacts, well, build system produces the artifacts, but the user may or may not care about retrieving them. And all of this is done in one repository. So let's talk a little bit more about what that means and what kind of challenges it poses on a build system. So when Google open sourced a build system, its internal build system, and open source that as Bazel, there were a lot of comments and confusions about why would Google, at such a large company with so many engineers, will use monolithic repository. Didn't we already move that away? Didn't we already decide there was so much contention trying to push to that? Didn't we already agree that it causes so many problems? So let's look at that in a little bit more detail. I'm not going to go into too many details, and if you're very interested about how we just do our source code in one repository, there is a great talk by Rachel Potvin that she gave at the conference Code at Scale that I highly recommend you check it out. So to me, working in one repository is basically a trade-off between having a repository of artifacts where now from all the different repositories that you have, you just put them in something like Maven Central, or it's building from source, because now you have just one source code, and so you can just build from it anytime you need it, a particular revision that you're interested in. And I assume that a lot of you are a lot more familiar with what it means to work in distributed code bases, right? Like many different code repositories. So today, everything is a trade-off, but today specifically, I would like to talk about the advantages of working in one repository, because I assume that you're a lot more familiar with all the advantages and disadvantages of working in many different repositories. So first and foremost, when you have a monolithic repository, that allows you to have a linear revision history. Every single commit is an atomic change to the code base. And so there's not really, the history is linear, so there's not really confusion about what happened after what, and having to worry about interleaving and causality, because all of that has been serialized. And this also allows us to have extensive code sharing and reuse, because everything can be cross-referenced. If I'm interested in deprecating my API and I want to figure out all the use sides of the function in the API, I can just look throughout the whole code base and figure out if the users are using it correctly and whether anyone is using it at all. It also makes it possible to do large-scale refactoring to modernize the code base. So if we decide that some base library that we're all dependent on, for instance, for manipulating files, needs to be deprecated because we know a better approach to doing things, we can actually do that across all the code base, and we can do this in a lot more informed fashion. And we can find all the different instances and just replace them. It's a lot easier to collaborate across teams now. So if I'm working on some new piece of code and I'm wondering what's the correct or better use of the API, what the best practices, I can look at other instances of uses of it, and I can figure out and even look at the history of how the team progressed towards a better implementation or better use of the API, and I can learn from their mistakes and from their successes. And also, if I'm interested in changing something in a library, I can just send a commit to the team, send it for review, and see what they think, if that aligns with their goals and their understanding of what the library should be doing, and then have that submitted as soon as it's possible. It also simplifies dependency management. So as we talked about, there's only one single source of truth, and so there's no confusion about the authoritative version of the file. When you have it in a central repository, if data gets corrupted, or if there are multiple versions of the same artifact, it could be confusing. Like, is this the one that the team actually wants me to use, or should I use the older one? What happens if I use not the latest version of it? Would that cause some issues that I should be aware of? Whereas here, it's a lot more clear. We can just specify that we depend on something and let the team decide what is the acceptable version that I should use. And there's no need to fork shared libraries. Now, if I need some feature, the chances are some other team or some other engineer might need the same feature from the library. And so we can work with the library team a lot more closely to get that added and make sure that everyone gets to benefit from this. And finally, we still have a way to distinguish between work-in-progress version that, say, the library team is working on and the released version, because we use something like code components for library releases, which is similar to Git subtree or Git subcomponents, where basically the team can mark it, OK, this is the released version, everyone should use this one, and this is a work in progress. We're still trying to figure out if it's something that we can release later. From the perspective of the build system, this also allows for predictable, repeatable build from source. So I know what my inputs are. I know what the source code looks like at a particular revision. And I can compare, build the same target multiple times and compare the outputs, the artifacts. If it happens that a different code path was taken through my build system, I should be able to, I should not see any results. The user shouldn't actually get to different binaries because, just because they took a different code path because my machine failed and I had to route them elsewhere, shouldn't actually cause any difference in the output. And so it's a lot easier also for me as a build engineer to detect that and find that and prove that there are some differences. And we still have a lot of optimizations to avoid compiling same artifacts. The biggest worry is that if we don't have a central repository of artifacts, then do we have to recompile all the dependencies again and again? Well, no, we don't, because we can just detect that something has already been compiled. And so we still can have very fast builds. And this also allows to decouple each team's processes as much as possible. For example, if I'm depending on some library on API, and there is a bug in it, but I need to release my code because my users are relying on me, I could just ask the team to tell me which commit I should cherry pick into my release and proceed with my release, while that team verifies that everything on their end is compatible and works as intended, and then release it at their own, on their own schedule and make sure that it goes through all the processes that they have in place. So we discussed what the build system does. We discussed some of the challenges, the scale, and some of the things that the build system should support when it works at Google scale. So let's talk about the distributed build system. How many people in the audience work with a distributed build system? I see a couple of hands. And you might actually be using Travis CI, maybe, for your continuous integration testing. OK, so distributed build system does very similar things to that. It's basically what the build system does is instead of now being on your desktop and you use like command line interface, now you send the request to a remote server. And many of the companies don't really need to have a distributed build system built in-house. And here's why. So let's look at how build system evolves and when the need arises to have a distributed build system. So we'll have a person working on a project that they're experimenting with and hoping something good will come out of it. And they will be building on their desktop using whatever build system that they're using at the time. And suppose that they're machine learning experts, and so they'll have a dependency on TensorFlow. And so their build system will have a way to download that dependency on their desktop, on their machine, and then build that and compile that and so on. So now, as the project becomes more successful, a whole team would be assigned to this project. And so now this team will set aside a box on the side, and it will do its build and testing and all the continuous integration testing on this box. Now, a different team might have the same dependency on TensorFlow if they work all in a machine learning company. And so now both teams have to have a box aside that they still have to worry about updating, maintaining, writing, making sure that all the bug fixes are picked up in the build system. And if have a bigger company with more teams, every single team now has to do this. So it poses an overhead. For machine learning specialists, it's maybe not their area of expertise, and they don't really need to worry about it, but they have to, because there's not an infrastructure for them where they can just delegate their builds. And so that's where a team like mine, BuildRabbit, will step in, where basically instead of having different teams having to maintain their boxes, they'll just be all in one shared infrastructure. And so a BuildRabbit team will provide the shared infrastructure where now teams can send build and test requests, and they can focus on what they do best and what they love, which is their machine learning projects. So let's talk about BuildRabbit now, which is the distributed build system at Google, which is part of the developer infrastructure team. BuildRabbit, the way I like to think about it, is basically Bazel in the cloud. So Bazel is the build system that Google open sourced, I believe, last year. And we'll see why I call it on the cloud. So in order to answer the question of what does BuildRabbit do, let's see where it fits in the build and test stack. So BuildRabbit sits very nicely in the center of the build and test stack. And it would be used by something like continuous integration system in order to be able to run the tests. And the release infrastructure will use it to be able to build the artifacts and then use those artifacts to be deployed to production. And all those orange boxes basically say that this is part of the developer infrastructure tooling, developer infrastructure bigger team. Now, other Google engineers and teams might want to do this. And so they're marked in a different color, not necessarily part of the developer infrastructure team, would want to do some building and testing on a remote server. And then integration testing framework might want to do this. So basically building the services and bring up those instances and then running integration tests against them. And BuildRabbit, in turn, will have dependencies on a source system. So we need to talk to the source system to figure out what is the state of the source system at the particular revision. If it was committed, then it would just pull it directly. And if it hasn't been committed yet, then it will use the overlay with the user's proposed changes. And now that it has the local environment set up, it will call into Blaze, which is Google's internal build system, where now Blaze would execute the build or the test command. And now it would put the artifacts into the build artifact storage, and BuildRabbit will know how to retrieve those artifacts and give them back to the user. And so now, Blaze, as I mentioned, has been released as Bazel. And so as you see, this BuildRabbit, it doesn't do the builds itself, doesn't run the test itself. It delegates it to Bazel or Blaze. And all it does is provides all this the distributed layer on top of that. It worries about what happens if machines fail, what happens if the user connection breaks from the machine that it allocated for the work, and so on. OK, so now we're on the same page about what distributed build system does. Let's talk about what it means to be building it at Google scale. So the build system went through a transition where it started out with one architecture, and then we started hitting the limits, and we had to redesign or architect it. And so it started out with a very simple client-server architecture, which I like to think of as a push architecture, and we'll see why in a second. So in a typical scenario, we would have a client library for the user that we gave to our users. And this client library will send a request to the BuildRabbit scheduler, which basically acts as a load balancer. And then it would get the response back for which worker should talk to. And now the client will request the worker to execute its workload, its build or test request. And then it would establish the connection, where over this connection, it would get all the build artifacts and the build progress information. So this worked really well for many years while we were figuring out what this distributed system need to do, distributed build system need to do for the company and for the engineers. What is its use case? So the problems that we started running into is that the client library was very thick, and it had a lot of logic related to routing and utilization of resources. The scheduler had some knowledge of that too, but also the client library needed to understand a lot of the transient and permanent issues inside the build system. And also now, the client library, if the connection broke between the user and the worker, we lost all the progress. And so the client library had to do the retries based on that. But what that means is for some of the big projects and big binaries with lots of dependencies, that meant that we had to try all over again, and we lost all the progress that we could have made. And so this was suboptimal, and so we moved to something called that we call build service, where basically we moved to the pull model, where before the user connected directly to the work and pushed the work onto it, saying like handle this build or test request. Now instead, the worker pulled the work off of the persistent queue. So the user will put its build or test request onto the persistent queue, and it will be just an event type of connection, event-based connection. And so now when BuildRabbit worker has resources available, is up and healthy, it would pick up this work, and so it would get that through an RPC from a persistent queue. And now there were two different types of outputs that we were producing. There was the build artifact, so the binaries that we built, and the build progress information. And so once the build rabbit worker produced those, it would produce the build artifacts and put them one by one as it was compiling and linking all the dependencies. And build progress information was like, if we're running tests, which of the tests failed, and which of them succeeded, and how far are we into our completion of our request. And so at this point, if the user was interested in getting the build progress information, then they could connect to it. And if either the service that provides the progress information or the user go away, that's OK, because the data doesn't go anywhere. As build rabbit worker produces it, it just gets persisted. And so the user can come back and figure out what happened in between it disconnecting. And similarly for build artifacts, if the user cared about getting the build artifacts, then it would try to, then it would connect to the build artifact service and get those. And so all the 4 components in green are basically what constitutes the build service. At this point, with the old facade, the API is still the same. The types of things that a user wants to accomplish with the build service are the same. But then we changed all the backends. We changed how we do this for better robustness of the system. And so comparing them side by side, this is what we had. In the old architecture, the user would push the work to the build rabbit worker directly. And in the new architecture, the build rabbit worker would pull the work off of the persistent queue. And in the meantime, user could query whether the build is executing or what's going on without losing that progress if it lost a direct connection. And so another interesting thing in this, at this point is how all the control logic happens, right? So in the previous architecture, we had resilience logic in the thick client library, where in order to understand a lot of the details of what it means to have a transient or permanent failure, did the user send a bad request for a file that would never compile, or did the worker go away and then it stopped executing the work, and that's what happened, and the user should just retry. Whereas in the new architecture, now we have resilience logic, which is centralized. And so I know it doesn't look like it's centralized because now it's spread over even more boxes. But conceptually, now all the build service owns all the resilience logic. And the user just sends very simple requests for putting the work on and requesting some of the outputs. And so we needed to move from one architecture to the new architecture, from the old to new. And there were many challenges associated with this. So as I mentioned previously, build rabbit sits in the middle of the build and test stack. We can't just ask users to stop building and testing. That's just not going to happen. And so what we needed to do is we needed to migrate from the old architecture to the new architecture. And we needed to do this with no downtime. Downtime was just a luxury that we couldn't afford. And so in the next couple of minutes, I'd like to talk to you about some of the key principles, key considerations that allowed us to do this successfully. I'm not going to go into too many details, but if you're interested, I've given a talk about this at Midwest I/O, specifically about how we pulled off migration with 0 downtime. But let's look at some of the key considerations in case you're doing migration anytime soon and you would like to know a little bit more about it. So first and foremost, we needed to ensure that we need to migrate backends first. And so the reason for this is, we started hitting the limitations of our architecture where we couldn't support quite as many users as we would like, and we couldn't support the load that they're providing on us. And so we needed to ensure that all of these new backends in the new architecture can withstand the load and can also do well with the expected growth of the system as the system becomes more robust, more fault-tolerant. And also what that meant is that we needed to leave the old facade up because we already gave out our client libraries to our users. And so they relied on particular functionality that we promised the build system does. And so we needed to do this with no user-visible changes whatsoever, because they still expected the build command would work exact same way it used to work, and the test command works exact same way it used to work. And they don't need to care whether now we have multiple different services doing the work that it used to. All it needs to be is invisible or even better experience. And so we needed to also focus on the mixed mode. So previously, because we gave out our client libraries to a lot of users, we promised that we would support it for some amount of time, because it's unreasonable for users to expect to keep up with our release cycle. We would like to release as often as possible, but we can't demand users to rebuild their binaries every time they want to do this, because that would interfere with their release cycles, and they have their own system concerns to worry about. And so what that meant is that we need to bridge between the old architecture and the new architecture and everything in between as we were transitioning from one to the other. And so we understood very well what the old architecture was like. We've operated for some time. We had much better understanding of what the system does and under which conditions it might behave wonky. And in the new architecture, we thought a lot about it. We designed it. And we understood where it should go. Now we needed to ensure that we can support all the transition periods in between. And so that's where most of the energy and focus and engineering time went in, to make sure that in between the transition, we still support all the old client libraries, and they still provide the same functionality, but now they work seamlessly with the new backends as they start coming up. We also needed to target launch-friendly clients. We couldn't just say, OK, now everyone, you're on the new system, have fun with that. And so what we needed to do is we needed to find specific users that would benefit most from using our new system. And so we could work with them directly and have their help to tell us if something looks bad on their end, and it might not look bad on our end when we didn't know that there is a problem. And so what that meant is that for the 3 different jobs, it was actually 3 different launch-friendly clients. There were some clients that only cared about getting the build artifact. There were some clients that didn't really care about any of that, and they just wanted the progress information of the build. And there were some clients that really needed the upgraded execution engine to be up to their needs. And so this ended up being 3 different sets of launch-friendly clients. And so what that meant is that we needed to decouple launch of services. We couldn't rely on any one of the backends, the new backends, to be up. And so because we also had 3 different sets of users that are launch-friendly users, we needed to ensure that for any of the backends that we were bringing up, they relied on none of the backends being up and running, and also all of them being up and running, and all the in-between stages. And it was essential for us to get maximum visibility into our system state. It's an expensive engineering effort to get the perfect laser view into what your system does at all times. But we needed to have something. We couldn't just launch something and just not have anything. And so we needed to have our metrics up, of course, and we needed to be able to query at any point in time and answer the question, is the system doing well? If it's not, what is going wrong? And so that was a lot of the trade-off and a lot of the balancing of, we could dump everything into info logs, right? And then just query them whenever we suspect something bad. But then, if something is going bad, good luck trying to parse through all the info logs and then, finding what's actually going wrong. And it was just a lot of balancing between, what goes into info logs, making sure that only essential information goes there, but also making sure that not just errors show up in the logs, that if we are successfully proceeding from stage to stage, that also shows up in logs, so we can know which milestone we're at and where exactly our system is stuck. And we had to practice the launches a lot. The launch that I led, which was for the execution engine, for the build habit worker, keying off of the persistent queue, that involves 5 teams across 3 different geographic zones and 2 different time zones. And so what that meant is that every single person needed to be in the loop. All the stakeholders needed to be in the loop about what's going to be the next step. Everybody's expectations needed to be set correctly so that they knew what to expect. And that meant lots of practice launches. That meant making sure that everyone is on the same page about what's happening next and which team should start paying more attention to ensure that their part is covered correctly, and so on. And so we created a lot of different checklists where, we created one long checklist that basically outlined exactly what steps we need to take. And also for engineering for resilience for people being unable to get online at the time when they need them, or people going on leave. We want to make sure that everyone knows what's going to happen in order to make the launch successful. And that also meant that we needed a solid rollback plan. If we were only 3 out of, say, 100 steps of the launch in, what does it mean if things go bad? How do we roll it back? And sometimes it was as easy as saying, take the reverse of the operation that you did. And sometimes that meant that the rollback was not trivial, and we needed to ensure that the right systems go back up at the correct time, and so on. Otherwise, the system will get confused, and it will be in the mixed mode that we didn't even foresee it could be in. So a lot of you probably, most likely, might not work on distributed build system, but I wanted to share a couple parting thoughts that hopefully you'll be able to use when you work on system and as you're building large-scale systems, not necessarily full-blown distributed systems, but any kind of system as you're planning the migrations and as you're planning evolutions of architectures. And specifically, I would like to focus on distributed versus centralized control plane. So control plane is just a fancy way of saying all the control logic related to, if this happens, what's next? And so specifically, let's talk about the distributed versus centralized control plane. I touched on it very briefly earlier, so let's look at it let's discuss it a little bit more. So with distributed control, that's what happens when we had an old architecture where our design works well for one machine, so for the CLI tool on one desktop, and then we scaled it to work on many different machines and to be able to send the build to remote server, many different remote servers. And so a lot of the logic ended up living in the thick client library that we gave out to our users, and so we needed to support all the different versions of the client libraries that we gave out. And what that meant is that it was very easy, comparatively easy to scale that up to many machines. But then the bigger overhead was during the evolution of the system. Because now we had all these overheads, we needed to keep in mind all the different previous implementations that we supported and make sure that previous client libraries that relied on them still work as expected. The opposite of that is having centralized control, which is what happened when I had the build system created. And so it was a distributed design from the very start. We anticipated exactly which component will be responsible for what, and what happens when one goes down, and how do we compensate for that, and what does fault tolerance mean in that context. And the bigger overhead was during the design phase. We learned a lot from our previous lessons, but still, we needed to make sure that we design it correctly, because once the design starts getting implemented and we realize that we haven't considered something major, that would be a big problem. That's essentially just throwing away all the work. On the opposite, the upside of that is that now we're able to evolve our architecture, evolve our implementation a lot more quickly, because we own a lot of the control logic in our system, and the user has very simple way of interacting with our system. And so things that we do can only improve it, but they don't have to worry about the details of the implementation. And they don't really have the client library anymore. They'll have a very much thinned out version of the library. So this is all I have for today about how we built a distributed build system at Google scale. I believe we have a few minutes, so I'd love to take your questions. Thank you. Yes, go ahead.
Just to make sure I understand you, are you saying on your repo you have Waze, Android, and Search code all in the same repo?
Yeah. So the question is, as I mentioned, we have a monolithic repository. Does that mean our search and all of our different products are in the same code repository? Yes, that is what I meant. Yes, that is correct. Which is actually pretty fun sometimes to browse around and see how people use and implement certain things. It's like, oh, I didn't know a search team did that. Yes?
So with the different languages in your build repo, are your clients putting in the event that goes into your persistent queue what their build software is, if it's make or if it's that instruction come from the client?
Right. So the question is, given that we support, it's a polyglot code base, do the clients just put the request? So the request is abstracted away, right? So it's not language specific. We use one build system, which was open source as Bazel. So everybody describes their dependencies in that way. But the build system itself supports all the different languages, all the major languages that are at Google supported, like Java, C++, Python, Go, and then I think there are a couple others that have lost presence, but are still supported by the build system, yes. And so all of them now, irrespective, so like we don't have different like Maven and Pip or something talking together. Now all the clients use one language, one protocol with which they express it, but then their code base, their source code will be in different languages, and we can do that, and we can compile that, and then can build it. Okay, go ahead.
Creating at least some elements of a tool chain which you're distributing at scale, presumably. Could you talk a little bit about how you do that with 30,000 developers when you're trying to push out the tools that you're creating?
Okay, so the question is, could I talk a little bit more about how, since we're distributing the client library to all the different engineers, how do we do that? So once we compile the client library, we put it somewhere. We have a way for clients to pick up the latest client library if they're interested. And it's a repository of packages where they can pick it up and use it by just rebuilding their binary and pointing to the latest. So now, so that was in the old architecture. With the new architecture, the idea is actually to simplify that a lot more, where it's just the commands they can send. And now, so we can basically extend this experience of submitting the command, and then that could go into the build system. But the basic idea is, once we have the client library that we would like our users to use, we put it somewhere and we tell them, anytime you want to update your library, you specify the version number, and then it will get picked up. So we have a whole different part of the build infrastructure, developer infrastructure that deals with that.
What's the operating system on the build machine?
The question is, what's the operating system on build machines? I believe it was talked publicly. It's Linux-based. The question is, are they all identical? It's a tough question. Are they, on the surface, they are all Linux-based operating system, but the devil's in the details and how we do all the upgrades and how we, make patches to all the underlying things that go into the operating system. Mm-hmm. Yes, go ahead. Okay, so the question is, for the source code repository, is that Git or something else? So Rachel Potvin goes into a lot more detail in her talk at the conference Code at Scale. It was based on Perforce, but now we have our own, which is called Piper. So you can learn a lot more about that in her from her talk. Let's see. Yes, I see a hand raised. So the question is the build system stateless? And so if you send two different requests, would it preserve some state in between those two requests?
No, if I give it a request today and a request tomorrow.
Mm-hmm. Right, so to clarify, if the two different requests are given, would it produce the same result? So we strive for repeatable builds, as I mentioned earlier. And so what that means is, if the request is to build at a given revision in the source code, and all the different variables are the same, it will produce the same result. So the build outputs will be the same. The artifacts must be the same. Otherwise, it's hard to tell which of the versions of the builds have I produced that is correct. Which one should I rely on? So we do provide repeatable builds. And then, obviously, if it's building at different versions, then it's going to be different if the changes in the commits affect it. Yes, go ahead.
Does that mean that
So the question is, does Google keep internal dependencies, internally, the dependencies that it might have on open source software? I can't talk about that today, but there's a lot of different security concerns related to that. And because our model is just not to have a central repository of artifacts, but to build from source, then that influences a lot of our decisions, instead of just saying like, oh, from lining in, just download at the given thing, at the given version. Any other questions? Yes, go ahead.
Does this build system build iOS and Android apps? How do you do that?
So the question is, does the build system build iOS and Android apps? So build system builds everything for Google. So every single product that you know about that Google has built, this build system builds it. And so the build system that builds is Blaze. And then Build Rabbit just provides the layer on top of that. And so anything that Blaze supports, Build Rabbit supports. Let's see. Any other questions? I think I might be able to take just one.
If my project depends on a library, do you version bind artifacts, or do you version bind like a revision in the code? It's all one.
So the question is, when defining a project, do we define the artifact that it depends on? Do we find the code? So, or do we find like the actual source code? So. I showed earlier a makefile where basically it's like the target defined and then how to produce the target. So the build language, you can look on bazel.io, it actually shows the example of a build file. It would basically specify very similarly a target and then a list of dependencies. And those lists of dependencies are also targets themselves. And so the build file would specify how to generate those and so on. And so then by specifying that, then the build system will be able to say, have I built this target before? And if I have, then it will be able to just link that directly without having to compile that. So it's all based on the targets. We don't store separate repository of artifacts, but it is a performance optimization that the build system is able to do by recognizing what it has built and what has yet to compile. So. Right. So then, so that part is about the components that I talked about. So the question was about, if the library gets updated, some dependency gets updated, how do I make sure that I have the latest one? And that's something that we give the power to the library teams, where they can now specify, and then the source system will be able to handle that correctly. And then Build Rabbit will be able to create the local view of what the source code looks like at that revision. And so if the library team released something, and in the morning I come in, it will get picked up if I'm building at the version that is past the time when they built it. Great. So that's all the time we have today. But I'll be around here if you all want to get donuts later and ask me questions as we go get donuts. Thanks for coming. Thank you.